Okay, it's a challenge, as Fisco, I think it was Fisco, not sure, indicate.
Yeah.
Okay, can you see my screen? My screen?
Yes.
Yeah. Okay. Yeah, about me, briefly about me, I'm a geologist with 22 years of experience. And I've been working in geometallurgy for about 15 years. Nowadays, I run my own company, AsGeoMin, with other colleagues, and we are specialists in audit and consulting. And I have a significant experience in machine learning applied to the mining industry also. Okay, and that's my LinkedIn. What is the aim of this session? Is discuss about the key aspects of the geometallurgy and metallurgy in the mining business, particularly in the exploration stages. Okay. The next few slides are about some definitions to feel more comfortable with these concepts. Okay, let's start with a definition for geometallurgy. Okay, geometallurgy is a discipline which considers the spatial variability, okay, of different processing parameters. The focus, the aim of this is maximize the value of our mineral resource in mineral reserves, optimizing decision-making in mining projects and operations, okay? So we will see that metallurgy, geometallurgy, and metallurgy are indeed quite different. In some sense, for me, are almost opposite in some sense, okay? We know from Wikipedia, metallurgy is the domain of material science, which is a studies for physical and chemical behavior. In our case, the focus of metallurgy is mainly in chemical, okay, and comminution, not alloys, okay? Alloys are the other leg, the other branch of metallurgy. Metallurgy has probably only two branches. One is the alloy, such as the steel, and the other is the metallurgical. We know this concentrator, leaching. Yeah, someone has actually. People has questions.
I think they got unmuted by accident, Christian. Please continue.
Okay, I want to continue. Yeah. So, in geometallurgy, we talk about geometallurgical units. I have a question. All of you guys are geologists or not? Someone is not a geologist?
I'm not here.
Okay, nobody. Yeah. So it's going to be easy, in my opinion, for you. Geometallurgical unit is a combination of geological units. But what combination? A combination that has a particular metallurgical response. Okay? So geometallurgical units are estimation unit of metallurgical parameters. For instance, metallurgical recovery, cyanide consumption. Okay, let's check this concept graphically, visually. Let's imagine, please, deposit, okay, or deposit. So in this deposit, we have two sections, vertical sections. The same section. On the one hand, we have the mean zone with the secondary sulfides on the top and beneath we have the primary sulfide. Okay. Lithology, same section. We have this. Okay, we have this porphyry and a rock wall as a rock wall and andesite. So remember, we said geometallurgical units are combinations of geological units with a particular metallurgical response. In other words, we combine, in this case, Minson and lithology for what? What purpose? For define geometallurgical units. For example, we have here a model for cyanide consumption. Okay, cyanide consumption. A model has 3 geometallurgical units. The first geometallurgical unit is high consumption and corresponds to secondary sulfide. Can you see it, this layer? With any lithology. The lithology is like transparent. Doesn't matter. Doesn't control the cyanide consumption on the top. It's only high consumption. So the samples we took here are of high cyanide consumption. Okay. The second geometallurgical unit has intermediate or moderate cyanide consumption. And what is the combination? The geological combination is primary sulfide and porphyry. Finally, we have a low cyanide consumption geometallurgical unit with low consumption, and the lithology corresponds to andesite in Minson primary. Okay, I'm going to put another example. This example is for comminution. Okay, cyanide consumption, it's about oxide, gold or precious metal, leaching. Okay, for concentrator plants, we use this index of energy consumption for ball mill. Okay, please observe that the same deposit has different combination. Can you see it? For these comminution parameters, respect with the cyanide consumption. In cyanide consumption, we have 3 behavior units: high, low, and intermediate or moderate cyanide consumption. For comminution, we have 4. So, can someone please tell me what is the combination of the geometallurgical unit 2 with intermediate or moderate hardness? Please go ahead. Don't be shy. What is the combination of this one? This one? I'm gonna this one. This is the laser. This one. This one. What is the combination of this one in terms of lithology and Minson?
It is the combination of
secondary sulfides and porphyry lithology.
Excellent. Good. Everybody agree?
Yeah.
Okay, perfect. So, can you see? Geometallurgical unit is geometallurgical model is not one model for every parameter. Depends on different combinations, different response, metallurgical response. Why? If we think about the phenomenology, that's the word, phenomenology, the behavior. Okay, let's think about the behavior. On the top, we have the cyanide, which is chemical, yeah, a chemical process for the ore, the interaction between the precious metal or metal and the cyanide, but comminution is a physical process, so it's completely different. So it's therefore we have different units, different combinations. That idea. This is a geometallurgical unit. It's very similar to a estimation units for assay, for zinc, for gold, for copper, whatever. Okay, but instead considering assay, we consider metallurgical response. Okay. Just a few minutes ago, we said something. We said geometallurgy is very different from metallurgy. Why? Let's check this concept, this difference. First of all, please take a look on the diagrams. On the left, we have geometallurgy. On the right, we have metallurgy. And please think about it. For geometallurgy, we have different samples. Usually, we can have hundreds of samples, okay? And all these samples, we take these samples hopefully in a representative manner in the deposit, okay? And we use one metallurgical standard for testing each sample. In other words, we take something like, give me 1 second, something like this one, like a ruler, okay? With this ruler is the metallurgical test, okay? With this rule, we measure all different materials we test all the different materials in the deposit. We collect sample.
I'm sorry, Cristian, I don't think I can see your sketch.
You can't see my sketch.
I can't, but I do see the laser point.
Okay. Anybody, can you see my slide, the slide?
Yes, I can.
Okay, thank you, Anissa. Adia, can you see the slide?
Yes.
Or not? Okay, okay. Okay, so in geometallurgy, we consider small scale testing is one standard for testing all the samples we take in the deposit, okay? On the other hand, for metallurgy, we can have one sample and apply to this sample different metallurgical schemes or parameters. For instance, we want to improve or try to figure out what is the best processing for a sample. This is a task for metallurgy. For geometallurgy, we don't want to know the best processing for each sample. We want to use the same standard to evaluate the contrast between the different units or zones. Which part of our deposit are, for instance, higher recovery or low recovery, high cyanide consumption, low cyanide consumption. That's the idea here. So as we can see, the aim of metallurgy is optimize, is try to obtain the best result. For geometallurgy, we don't want to necessarily obtain the best result, is try to compare the different zones or units in the deposit. Okay. One important thing we need to bear in mind, especially in exploration stage, is this one in the box. Geometallurgy requires a standard. Okay. Geometallurgical testing needs a metallurgical standard. Metallurgical standard is, for example, if this is the flotation test, how many minutes the samples going to be into the cell? The percentage of solid, the mass and number of steel balls in a combination testing. So for geometallurgy, we need a standard. We will see that the problem with exploration is the following. We don't have a metallurgical standard because we don't have a plant or a definitive plant for our project. Okay. So what can we do if we don't have a standard? That's the thing in exploration. Let's continue. Let's talk about the project stages. Okay. Okay. Maybe all of you, or hopefully, have seen this before, or something like this one. Here we have the different project stages. Okay, from conceptual or scoping study stage, pre-feasibility stage, and feasibility. This is the stages for the project. Important concept: as the project stages advance, the accuracy, which is in here, the accuracy is better. The accuracy increases, and the number of scenarios, okay, decrease. When we start with a project in exploration, for instance, in a conceptual or scoping study, we have several scenarios. For instance, for treatment, for processing the ore, maybe we will have a concentrator plant with a flotation, or maybe not. We have an option with hydrometallurgy, with heap leaching, or bio-leaching, etc. Okay? So in conceptual study or scoping study, we have several scenarios for ore processing. Even for the other discipline also, for mining, for environmental, social, okay? In pre-feasibility, we eliminate, at the end of the conceptual or scoping, we eliminate some scenarios. We select some of them. We increase the precision. We reduce the uncertainty. And by the end of the pre-feasibility study, we select only one option for everything, for mining, for everything, and for processing. So in feasibility study, we are sure about the type of processing, okay? The ore processing. We are talking about concentrator, flotation, and not if this material could be processed via hydrometallurgy. So this option was rejected. Okay, we have only one option, and we need to refine that option. What else? Obviously, this feasibility study is very important because we have here a final decision. This decision point is about design and construction. When we move from scoping study, pre-feasibility, and feasibility study reduce the uncertainty, but that has a significant cost. When we move from here to here and finally here, in every stage, we spend more and more, okay? So to reduce the accuracy, to improve our precision, we need more and more money, okay? So this is our project stages, but we are here talking about exploration. So imagine, we are in the best scenario, we are talking about conceptual study or scoping study. This is for exploration. And exploration, as we know, is the kingdom of geologists. Yeah, the geologists are queen and king in this stage, the exploration. What about metallurgy and geometallurgy for the different level of study? Starting with the scoping study. Here we are discussing today about exploration and scoping, or even before scoping. Please have a look on this one. For scoping, for exploration, we only need a preliminary reconnaissance of potential variables that might impact the project processing. So the important thing in here is we don't necessarily need a geometallurgical model. Why? Because we still don't have a metallurgical standard. Even the processing colleagues can be thinking in, we have an option A with hydrometallurgy and an option B with concentrator. So since we don't have a metallurgical standard, we can make some important things about the processing of the ore. Okay, we will check that in the next slides. Okay, when we move from scoping to PFS, we're starting with defining some our geometallurgical units. In feasibility study, we definitely need geometallurgical units. Okay, and that's the thing. We are in here in exploration. Okay, so we don't have yet a geometallurgical model. Okay, a block model with metallurgical parameters, but we can do some activities in advance to support the metallurgical definitions. So for scoping study, the idea is, for exploration, is establish a general understanding of the ore body and an outline for the processing that will be eventually used for extracting the valuable minerals. Scoping study, the exploration stage, provides a base for decide budget and the possibility of future metallurgical testing. So the question is okay, we don't have a proper metallurgical or geometallurgical model because even we don't have a metallurgical standard, but what can we do for the moment in exploration? One thing we can do is orient, okay, the different characterization, logging, chem scan or test scan, whatever, microscopy, assay, orient, put this characterization not only thinking in geological and grade estimation, okay? Not only thinking in grade estimation, thinking in the processing ore. So when we make this geological logging, we need to think about what features, what variables or features of our ore can affect the processing, such as clays, limonites, habit, mineral zones, lithology, structure. So we need to think about it. We need to think and understand what is the potential effect. If we think about the bucket, for instance, we need to think in the abundant clays we have into your bucket. These clays, depending on the type of clays, could have an enormous impact in some specific process of the ore. We will see later in the thickeners, the filter plant, in the mass recovery in the flotation process. To your bucket also contains large amount of pyrite. Pyrite is a competitor with the chalcopyrite or other ore during the flotation process. So pyrite is as an important mineral for processing, even considering that pyrite does not contain copper. Okay, so if I am a 2D bucket geologist, I can recognize that type of features that could affect the processing. And the geological logging needs to register, to record that type of information in a manner that could be useful for the understanding of the processing. So as a geologist, we have a big responsibility for the processing, because we have to make these warnings for the operation, for the processing guys, for the processing colleagues. We can identify which features of our deposit can affect the processing of our ore. If we move from an oxide or we have, for instance, a top of sulfides. Below the top of sulfates, probably the comminution, the throughput, the rock going to be much harder than above the top of sulfates. That type of key elements, primary elements, is important. We make warnings to the processing colleagues. Another characterization, which is very important, is the automated metallurgy. Why? Because, as we know, this type of studies can report many things. We can customize what we need. So when we send this type of samples to this type of characterization, it is important to bear in mind the impact of this one in the processing. For instance, it is important maybe to understand the association between gangue, between pyrite and the ore, or maybe the habit, or maybe the enrichment in the different submerging zones. As we know, this equipment combine electron images captured point by point in a regular grid in the sample. This is the sample. We have at least, as far as I remember, 70,000 points. It is based in this is not optical, as we know, this is electronic. We have this electron beam and the response from the material in the sample. Particularly important are these backscatter electrons and the X-rays. Here we have two ChemScan with the EDS detector, this cylinder here for the X-rays. So we have this backscatter electrons generating this image in gray, which depend of the atomic number of the sample. So immediately the equipment, the device, identify this black, which corresponds to the plastic. I don't know what's the name of this. And the mineral particles are the grays. And these probably are ore based on the lighter gray hue. On the other hand, we have here the other important emission from the sample, which is the X-ray, reporting the chemical composition of every point, every 70,000 points of the sample. And as we know, we have here the wavelengths and the count. We can obtain this type of images, false colored images. It is important to bear in mind that, as we previously discussed, we can ask almost anything to the ChemScan, to this type of study. So it's important to understand, for instance, if we are thinking in sulfides, the liberation of the ore, for instance. So it is important if we send a ChemScan or this mineralogical studies to ask for liberation. Okay, not only for the mineralogy, not only thinking on what is the mineralogical species here? No. What are the associations? What are the size? What are the liberation of the ore? That type of questions needs to be answered. Okay. Let's discuss about some study cases. The first one is about the impact of clays on slurries. This is an operation in my country, in Chile. Chile is located in South America, in the southernmost western coast in South America. The northern Chile is a very narrow and long, it's like a strip. It's very long and narrow. And in the northern part is the Atacama Desert. Atacama is this one. As far as I know, it's the driest place on Earth. So imagine the importance of water here. It's there in the Atacama Desert. It's very important, the water management. So what are slurries? Slurries are suspensions. In other words, heterogeneous mixtures of a fluid that contains solid particles sufficiently large for sedimentation. So this is not a solution, obviously. Yeah, solutions are ions. This is suspension. This is particles. Two important properties of this slurry or suspensions are the rheology and the sedimentation rate. The rheology allows us the understanding of the relationship between the stress, okay, the shear stress, and the strain, the deformation of the fluid. So, in other words, it's like how many energy we will need, or how much energy we will need to move that fluid, that suspension in a pipeline, okay? And sedimentation rate is a very important parameter. Both are very important for the transport and decantation of this suspension. Here we are observing these thickeners. I don't know if anyone is familiarized with these thickeners. These thickeners are tanks, very shallow and wide area tanks. The idea here is we send from this pipeline, through this pipeline, we send the slurry, the tails of the process, and we put these slurries in here in this decantator, in this thickener, and on the top of the suspension, we will obtain clear water. Okay, on the bottom, the decantation process occurs. So we obtain from here, we recover part of the water of the process. Okay, this water comes back to the process. In this manner, we don't have to have only fresh water each time we process an ore. Okay. So what is the impact of clays on these slurries? Look at this. This is a core, a piece of core. We have these clays. I don't know if it is possible to see these clays. Look how these clays are absorb water. Can you see it? So there are here 7 samples, okay, 7 samples. In here, in the red, we have the clays, the clay content for the 7 samples. And the sedimentation rate is on the left, this axis. So what can we observe here? What do you observe? What is the relationship? Is there any relationship between the clays, the content of clays and sedimentation rate? What do you think?
The increase of the content of the clay will impact the sedimentation rate, right?
Right, exactly. It's like inverse, shall we say? So at some point, maybe I don't know, 5% or so of clays will reduce their sedimentation rate. What is the importance of this? Well, if the content of clays is high, we will need not only 1, but maybe 2 or maybe 3 thickeners, because maybe 1 not going to be enough for processing all the slurry, okay? Because the sedimentation, the decantation will be slower. If we don't understand this relationship, maybe it's very possible metallurgists can make a benchmark and say, no worries, we will design only 1 thickener for all the process. But when we move from the project to the real world of the operation, maybe we have instead 5% of case, maybe we have 15. In that case, this thickener not going to be able to process all the ore, and we will need to process less material, less throughput. Please consider all the material that is the tail of the flotation process pass through these thickeners. All of them, all. It's like a bottleneck. We cannot work, we cannot operate without these devices, okay? So we can observe here a clear relationship between content of clays and sedimentation rate. Similar study case B, even not only clays. If we, this is a deposit in Chile, very, in my opinion, quite similar to Tuyubuque, or at least at some part of Tuyubuque. We have in here the following. We have 4 elements in these triangles. The illite, pyrophyllite, and kaolinite. Okay, content, relative content in this triangular diagram, and colors represents on the left sedimentation rate, on the right the shear stress on the right. This is a Spanish word. I forgot to change. It means right. Okay, and the points are samples. Okay, these minerals were determined via XRG. Okay, so please tell me, what can we see here? What can you see? How can we interpret these charts? I don't know if this is understood, the idea here, or do you have any question about the diagrams? Let's take advantage of our precious moment. Remember, we are almost 50 persons in here, and let's take advantage of that, of sharing, of discussing. Don't be shy. Go ahead. What do you see, or do you have a question about these diagrams?
I have a question, please.
Yep. What is that?
So let me introduce myself. My name is Jeffrey. I'm working in a smelting company, but I'm also a half geologist doing things like this, but for nickel. I'm curious for this model. How do you make this model? Because this is in ternary diagram, and it's quite interesting. You have a straight line, like for example the right one. You use the coordinate percentage to measure the shear stress capability. Yeah, that kind of interpretation. Can you please explain? Thank you.
Yeah. This, as Jeffrey said, this is a ternary diagram. So maybe all of you are familiarized with this type of chart. So we have on each vertex of the triangle, we have a mineral species. This is kaolinite, this is illite, and pyrophyllite. So when we are here, forget about the colors for a moment, okay? Only thinking in the triangle. In this vertex, if we have a sample here, let's talk about these two samples, these samples over here. These samples contains mainly of the three species, mineral species, contains almost only pyrophyllite, and just a bit of kaolinite and illite. This sample here contains mainly, chiefly kaolinite, okay? And this one here contains mainly illite, a bit of pyrophyllite, and zero kaolinite, okay? So we have the endpoints of these triangles are the pure species, illite, pyrophyllite, and kaolinite, and the white dots are the samples which we took in this deposit. So we don't have yet here a model. We only have these samples, these plots of the samples. And in addition, we have a fourth dimension. The fourth dimension are the colors. So the color represents a metallurgical parameter. In this case, on the left, the sedimentation rate, what means that samples with kaolinite, or majority or mainly kaolinite, express more or a higher sedimentation rate. So are better samples, better material for the process. On the other hand, sedimentation rate is decreases when we increase the amount of pyrophyllite and illite. Okay? So, should we say kaolinite is better for sedimentation rate, and when we move to materials with pyrophyllite and illite, this material show a lower sedimentation rate, which is bad for the operation or bad for the project, because involves more capex, more investment, higher cost. Okay. The opposite is for the shear stress. When we have kaolinite, we have a lower shear stress. When we have pyrophyllite and illite, we will need more energy, more power in our bomb to pump the slurries. So again, kaolinite is better in terms of shear stress. We need less energy to move this slurry, the slurry with kaolinite instead pyrophyllite and illite. I don't know if, Jeffrey, I respond properly to your question.
Thank you for your explanation. It's really clear. So basically, you are interpreting based on your smelting process that kaolinite have higher rate of sedimentation and also lower shear stress. I understand.
Yeah.
But honestly, I quite it's interesting to see them. So you base on interpretation, not by data. Is it like? Is it that?
Yeah, it's an interpretation based in this XRD results. Remember, each geometallurgical sample, each of these dots, white dots, it's a geometallurgical sample with a characterization of sedimentation rate and shear stress. In addition, these samples were characterized via XRD, X-rays, okay, for determine the gangue mineralogy.
Okay, quite clear. Thank you, Cristian.
You're welcome, Jeffrey. Okay, we can come back to this slide at the end. I would like to talk about the flotation process. Maybe not all of you as geologists understand completely or the flotation process. So this is a very interesting scheme, in my opinion. Okay, how the flotation process works. Flotation process allows us the separation of variable material, this in our case of zinc or copper, whatever sulfides, okay, generating a slurry, a tailing at the bottom. So this is like a tank, okay, of metal with three phases. We have three phases: liquid, gas, and solid. The liquid is water, the gas is air, usually it's air, and the solid is our particles, okay, our mineral particles. Previously to the flotation, we need to crush and grind the material for generate separated particles of sulfides, and ideally other particles of gangue. Okay. What is the phenomenon? What is happening here in the cell? Well, we have this impeller. This is rotating here, and we add air through this pipe. Okay, we have air. So we have liquid, water, gas, which is the air. We add some reagents like frothing, collecting. For what? For generate these bubbles, this one. Can you see it? We create these bubbles of air and add some organic reagent. For what? For increase the hydrophobicity of the sulfides. Naturally, the sulfides, like a chalcopyrite, are hydrophobic mineral. Okay. When we add some reagent like collector, we increase the hydrophobicity of the chalcopyrite. What it means? The chalcopyrite going to be attracted or to the air, or terrified or frightened, shall we say, for the water. So the sulfide, the hydrophobic particles, will attach to the bubbles. Can you see it? And the air moves to the froth phase here and is collected in a channel. So we put more material here. On the top, we obtain our concentrate. How? Taking advantage of this hydrophobicity of the sulfide, they attach to the bubbles and move to the collection zone to generate our concentrate. That's the basic idea of flotation. Do you have any question about this? Is it clear? Is it not clear? What do you think? Gayu? Is it clear, Caillou?
Clear.
Okay,
Let
excellent.
me Google.
Vicky?
I think it's
Is
quite
it-
clear and quite intuitive, but thank you for putting it so simply.
Thank you. This is not my my feature. Another person do this for us. This is the source, okay, of this diagram. This is, yeah, it's quite clear, in my opinion also. Yeah. So remember, we have this hydrophobic sulfides and the hydrophilic minerals. Hydrophilic is the gangue, mainly the gangue, okay? And hydrophobic are the sulfide, like chalcopyrite, molybdenite, or pentlandite for the zinc, guys. Okay, that's the flotation process.
Christian, can I ask something?
Yep. Yeah, please
How,
go ahead.
okay. How do you know which minerals are hydrophilic and which minerals are hydrophobic, or oh yeah.
Okay. It is well known that the sulfides are able to, or are, how can I say this? Yeah, it is well known that sulfides are hydrophobic, okay? And in general, phyllosilicates are hydrophilic. And when we add this collector, this reagent, collector are organic molecule that works like the soap. When we wash our hands with soap, I don't know if you know, we use this organic chain molecule that surround the dirty particles and generate this froth. Okay, the froth take this dirty from our hands. It's like this one, indeed. When we wash or rub our hands, washing our hands, it's like this one. It's a reagent, an organic molecule which surround the dirty like this one. Okay, so the dirty particles in our hands are like the sulfides, are removed for the bubbles. But to answer the question, the sulfides are hydrophobic and the gangue are hydrophilic. That is the an important property. And in my opinion, the person that invented this process was a genius, because it's really simple and really effective. Actually, this process has not changed in the last, I don't know, 100 century, more than 100 years. It's more or less the same process, because it's really clear how the sulfides are hydrophobic and the gangue is hydrophilic. This property is really clear, and it's incredibly important for this process. Okay. Okay. One important property I would like to consider in this case is the relationship between the grade or the quality of the concentrate and recovery, because we need to consider not only the recovery, but also the quality or the grade of our concentrate. So if we are working in a pentlandite operation for nickel, we need to reach some grade of nickel for the concentrate. Okay, we can't sell a concentrate of 1% of nickel or another concentrate of 10% of copper because it is not possible to sell it. Okay, nobody wants to buy that type of concentrate. So we need quality, which is the grade of copper, zinc, whatever, and the recovery. Remember, the recovery is the percentage of the metal in the original feed that is recovered in the concentrate. So recovery of 90%, what means? If I have a kilo of sample and the concentrate contains after the flotation 900 grams of metal, then the recovery is 90%. Okay, this is the concept of recovery. So look at this. This is important. When we have, look at this. The black is the ore. For instance, the pentlandite, the black, or the chalcopyrite, or the sphalerite here. But we have some particles with mixture of ore and gangue. Can you see it? White. So when recovery is low, is in this area, we can obtain pure particles of our ore. So the grade is high. You see it, a concentrate with black, in this case with ore mineral, but the recovery is low. If you want to increase the recovery and recover these particles, what happened? Look at the illustration. We increase the recovery, but what happened with the grade? The grade decreased. Why? Because we are putting in our concentrate, we are recovering not only pure particles of the ore, but mixed particles of ore and gangue. So can you see there's a inverse relationship between recovery and grade? So we cannot do everything, or we recover, or we maximize the recovery, or we maximize the quality of the concentrate. That's the reason because flotation is divided in two stages, two main stages. The first stage is the rougher flotation, or primary stage, in which the focus is the recovery, this one. Try to recover as much as possible. And when we have this rougher concentrate, we move to the second stage, which is the cleaner. Okay, we regrind the concentrate, the rougher concentrate, and put the focus on the grade. In the case of copper, we need at least 27% of copper for selling this concentrate. Okay, so remember, we cannot have in one process high recovery and high quality. Is it clear, this slide, this concept? Satria, is it clear?
Yes.
Yes, excellent. Andrei?
Yes, it's clear, Mister.
Okay, perfect. Okay, this is very important concept. Why? Let's check this concept from our point of view as a geologist, okay? Let's check this as a geologist. As a geologist, look at this. What is the impact of the habit of flotation process, this mineralogy? Look at this. This is a microphotography, as we know, of, in this case, digenite, copper sulfide, and limonite, iron oxide. Yeah, as we know. Look at the small scale intergrowing between these two species. Can you see? So remember, digenite is hydrophobic and limonite is hydrophilic. going to be really difficult in this case for this particle to float, okay? Because the flotation process, as we know, remember, or maybe I don't mention, this is a surface process, physicochemical is on the surface of the particle. So in this case, we have probably most of this particle is limonite, and we want to lose this particle. It's going to be really difficult to float this particle. So can you see it's impossible to obtain 100% of recovery? For instance, for this type of texture. Look at this. We have gangue and chalcopyrite. So chalcopyrite is covered, surrounded by the gangue. What's going to happen here? What do you think? This particle going to flotate or depressed or sink? What do you think?
I think it will sink.
It will sink.
Yeah, sink. And what happened with the chalcopyrite? Chalcopyrite going to the thickener, and after that to the tail down. Okay, so we lose that ore. Okay, another example, penalties. So the concentrate, the smelting process, depending on the smelter plant, we requires concentrate not only with quality on the grade of the ore, like nickel, copper, molybdenum, whatever, but also with low amount of certain elements, deleterious elements, such as bismuth, mercury, arsenic, typically. So look at this, please check these particles. We have this small scale intergrowing of digenite, in this case is digenite, cobellite, and energite. Here, this particle of energite inside digenite, cobellite, and chalcopyrite. So what happened here? Imagine what's going to happen with this particle. This particle is hydrophobic. So going to be attached to a bubble, going up, and going to be recovered as a concentrate. But the energite will add arsenic to our concentrate. Okay? And what happened with the arsenic? When the arsenic increase over some limit, there will be some penalties. So they're going to pay $1 for our concentrate, but they're going to say, here's your $1, but wait, no, it's not $1, there's a penalty. It's only $0.95, not $1.
What? What? No!
Yes, indeed. It's true. It's true, Mark. The penalty is true. So when we are in an exploration project in a high sulfidation deposit of copper or whatever, zinc, we identify a significant amount of sulfur salt, we need to think, okay, as an exploration geologist, wait, energite has really good flotation. It's a really good flotation. So, I mean, energite floats really good, really well. So probably this deposit going to generate a concentrate with a significant amount of arsenic. So I need to bear that in mind and discuss with the colleague of process, the processing colleagues, okay? Because we have this energite identified by the geologists in the earliest stages of the exploration, from the beginning, even without microscope or chemical analysis, a geologist is capable to recognize the type of minerals. Okay. Look at this. What do you think about this one? What could happen here? Who can tell me what can be happening here? We have, look at this, we have pyrite, okay, and inclusions of ore, such as bornite or digenite. So if we float, if we recover this bornite and digenite, we want to affect the quality of our concentrate. We cannot float this all this pyrite, because if we float all this pyrite, the quality of our concentrate going to be really low. For instance, do you bucket? If we have, I don't know, 5%, 8% of pyrite, we cannot float this pyrite because the content of this pyrite is really low in copper or zero. And necessarily we want to lose this bornite, this digenite as inclusions in the pyrite. And this is the last slide. We have magnetite. Look at this, it's magnetite surrounding these ore particles. So again, we're not going to be able to recover these particles. So in short, in exploration, or to sum up, in exploration stage, since we don't have a metallurgical standard, we are not sure about how the ore is going to be processed. We are not able to produce or generate a proper geometallurgical model, okay, with these geometallurgical units, but still we can think about how our primary elements on the rock, such as ore mineralogy, gangue, textures, mean zones, lithology, RQD, FF, GSI, can affect the processing of our ore. Then, as a consequence, when we do any type of characterization, such as logging, mineralogy, assay, we need to think about it. Okay? We need to think how to take advantage of all this technology, all of this information, all this data, and keep in mind that we need to take advantage of this characterization for not only understand the geological process, but also give some guidelines, some advice, some warnings to the project in terms of the processing of the potential processing of that ore. That is my final comment, and we are now able to discuss or make some questions, comments. Feel free.
Go ahead, Mas Fisco.
Yeah, Christian, thanks for the presentation. It's really interesting one. I have several questions regarding the geometallurgy for the exploration stage, especially for other.
We lost Fisco.
Yeah, I think it's a connection. He's having a connection trouble. You can wait.
Hello?
Mas Fisco?
Halo?
Ya, halo, oke. Silakan dilanjut, Mas.
Okay, Christian.
Yeah.
Regarding the geometallurgical test for the exploration stage, maybe it's common for the hard rock one, such as copper, iron ore, and gold. We have a mineralogy analysis, which is a quite detailed one to tell about the characteristic of the ore. Yeah. But in other hand, what about the nickel laterite? Yeah. As we know, now we have a new method using the HPAL to process the limonite to extract the nickel and the cobalt. Unfortunately, in the exploration stage, we don't have enough information to do the analysis. Could we select the sample based on the chemistry alone to do the geometallurgical analysis?
That's a really good question. Honestly, Fisco,
Yeah.
I only have experience in nickel in orthomagmatic deposit. So, unfortunately, I'm not sure. I have no experience about this type of deposit. So I cannot say, unfortunately, if geochemistry going to be enough for this characterization. Sorry, but
Okay.
I don't know.
Thanks. Yeah. Okay.
Maybe I can help you, Christian.
Yeah, please.
Fisco, are you working at nickel industry? Okay, but maybe I can share something from my experience in HPAL smelting industry. So basically, during exploration, because I was starting from pre-feasibility study, and we have already done what we mean by metallurgy drilling. So this metallurgy drilling is focused on collecting samples, a lot of samples, just to test for the metallurgy, try to testing with every process and other factors, like for example, H2SO4, sulfate, and also flocculant, and also limestone, to get the most effective and also the most high recovery model to get what we want as a geologist during exploration, to make a model and also to understand the condition. Is it economical or not economical? Maybe we can discuss more about this, Fisco.
That could be nice if you can discuss Jeffrey with Fisco. I think would be awesome. Thank you. Thank you for your experience, for sharing. Jeffrey, thank you.
Okay, if anyone else, for everyone else, you can ask your questions by unmuting your mic or in the chat. Go ahead and don't be shy. Maybe while we're waiting, I have a question. Can you go back to the stages slide in the beginning? Project stages, yeah. How long does the metallurgical side, in terms of planning, how long the metallurgical side usually takes?
It depends on the several things. Okay, there are some companies that are they take more risk in general. There are companies more conservative. So I know some companies that from exploration to the operation, all this pathway take something like 7 years, which is, in my opinion, really fast. And others companies double, almost 15 years from the exploration to the construction. In addition, some companies like Anglo-American, even don't have this PFS. They speak about PFS A and PSF B. Okay, but I would say that at least each stage would take a couple of years in investigations. And as we know, from 100 or more probably exploration projects, only one finished as an operation. So even I know maybe you two projects with decades of history, different stages, different companies, and 2 decades or 20 years, 30 years still as a project. But if the project is really interesting, really good in terms of financial, like NPV, this type of indicators, yeah, I could say a couple of years of investigation for each stage at least.
Okay, thank you, Cristian, and so sorry for the noise. We also here have our seniors and experts like Pak STJ, Prof. Mega, Dr. Arifudin Idrus, welcome and thank you for joining. You are very welcome if you want to ask some questions.
Yeah, Nadira is working in the airport, in the landing of the aircraft. Yeah, please go ahead.
Okay, Pak. Sorry. I just want to know this, as I know, for sulfide ore zones in high sublimation deposits, it's not economics until now to be processed.
Okay.
Does any studies that can make ore sulfide zone of HS deposits become more economic, Pak Cristian?
Yeah, Farid, the question is.
Okay, until okay.
Sulfidation. Yeah.
Okay. In Indonesia, we process the ore metallurgy in high sublimation systems is more with leach process, with leaching process, including fan leach or heap leach. Does the because it's more economic, then we process with CIL or carbon in leach. Okay, now in sulfide ore of HS deposits, until now I didn't heard the company processing the sulfide ore of high sublimation deposit type. Does any studies that makes the ore the sulfide ore in HS deposits becomes economic, Pak Chris?
Okay. What would be the problem with this processing? The arsenic or what?
I don't know, because my background is low sublimation systems. I don't know what it with high sublimation systems metallurgical process, but I heard from an experienced geologist, from metallurgists, that they have or it's not economics to process the sulfide ore of high sublimation deposit system.
Okay, yeah. I have an experience in this case in my country. There's a high sulfidation deposit with a mine actually operating in my country in Chile. The name, if you want to look for that, is DMH. The MH is for Ministro Ales with the H. It's like the name of a former minister. And this mine is high sulfidation, really, really high sulfidation, but for generate economic concentrate, considering the high arsenic in the feed, because it's energite mainly, there's an intermediate process which is roasting. So they roast the concentrate and vaporize or transform these minerals, the energite, removing the arsenic as a gas. Okay, in a closed tank, recover the precipitate the arsenic as a scorodite, and this ash, shall we say ash, of ash concentrate is sending to the smelting, but removing most of the arsenic. In this manner, this deposit can produce commercial concentrate, despite this energite in the feed. This is my experience in terms of high arsenic content. So the way that this company, the name of the company is Codelco, remove the arsenic to produce a commercial concentrate is roasting the concentrate. Okay.
Okay, but how about we Marsabe, as we all know that as deposit type, they have an artificial oxidation process, what?
Okay. Yeah, that's interesting.
Okay. With the purpose is to make the ores to become oxide, but hence it's good process by leachings. Does any studies but in the other parts of the world about artificial oxidations type?
Okay. Yeah, I'm not familiarized with that type of process. And one important thing to focus on is I'm talking in general as a geometallurgist. Remember, it's important to understand that we as a geometallurgist, we depend on the definitions of the guidelines of metallurgists. Geometallurgists don't create the rules. The rules are made by the processing guys. Okay, this is an important thing to understand in this case. I see Budi. Budi, again, how are you, man? Budi?
Pak STJ Budi,
Budi?
apakah mau bertanya tadi?
Budi, are you the Budi I know from a previous session? I'm not sure. Budi Santoso, yeah, Budi. Budi is maybe. Okay.
Sorry, Chris.
Yeah.
Was it me? I don't remember, but I really enjoyed the discussion that you had with Farid.
Okay. Okay.
Yeah. Sorry, I think what we are talking about, Farid was talking about, is the high sulfidation system in Indonesia are mostly a gold system that now in production. But maybe very soon there will be a combination between high sulfidation overprinting the porphyry. So we're talking about the energite and also some copholites. Maybe the subject or the experience that you're sharing will be very beneficial to some of the project that now being developed. But the thing what Farid was talking about is the gold high sulfidation. For your information, most of the high sulfidation operation in Indonesia are mostly extracting the oxide gold.
Gold.
And the sulfide gold is too difficult. It's either kind of refractory, the grade is not so high, the cost to do the roasting is too high as well. So maybe that's not only the reasons why they are not economic, but probably the grade is not high enough.
Got it.
And, yeah.
Thank you, Bodhi, for the clarification. Yeah, now I get it. Yeah, it's gold, oxide gold. Okay, cyanide, all of this. Okay, yeah, thank you.
One very simple question is about maybe in your experience, when actually we what is your experience when actually your team, the geological team, exploration team, start collecting the preliminary metallurgical sample for met test? Is at the very beginning of the project, or anywhere when basically you have already delineated the resource, Chris?
Yeah, if I understand the question, the first thing we need to do before starting any geometallurgical sample, when we talk about geometallurgical sample, we are talking about small samples taken from drill holes. Okay, small, and we don't want to mix samples, or we don't want to composite samples in the space. We have one sample in one spatial position. Okay. Before do that, we need to conduct a metallurgical campaign. Metallurgical is the first thing. Metallurgical for metallurgical research, metallurgical investigation to define what is the best way to recover our metal in terms of if it's flotation, in terms of size of the particles, in terms of time in the flotation cell, what regions and in which amount we will add to the cell, and other parameters, metallurgical parameters. So for this investigation, we firstly need to conduct a metallurgical campaign. For metallurgical campaign, usually we take large amount of samples. So we move from, to be clear, I forgot to say that. When we talk about geometallurgical samples, we're talking about samples between, for flotation, okay, for that process, between 40, 60 kilograms. For metallurgical characterization, we are talking about hundreds of kilograms, even tons of samples of tons of material. And in this case, obviously, we need to mix pieces of drill cores from different locations. In metallurgy, we want to represent a global, okay, a global behavior to understand representativity of entire year of production, entire zone, okay, or lithology or whatever, okay? This is the first stage. So metallurgical campaign with hundreds or even tons of samples is required. Based on this metallurgical characterization, based on this, we can say, or processing colleagues can say, okay, we are going with flotation. We can conduct some combination testing. This is the options for granulometry, these 2 or 3. And based on that, we can start from these definitions with our geometallurgical characterization. The big difference between geometallurgical and metallurgical characterization, besides the size of the samples, is in metallurgy, we composite, we mix samples from different positions, different drill holes. In geometallurgy, we don't do that, okay? Because we want to understand the local viability of the deposit in terms of metallurgical response. I don't know, Budi, if I answer your question, or maybe
Yes, I think that is very clear. What we usually do, or at least in my previous company did, was for the geometallurgy samples, we did a geological domain first, because as you mentioned in earlier slides, that basically the ore characterizations need to be defined very carefully from very beginning, whether if it is due to its original host rock, the alterations, gangue minerals, and the deportments of the metals, for instance, gold. So I think that's very emphasized or amplify what you have explained before. Chris, the geometallurgy is very different to the metallurgical test when we are already in the close to a production stage. So I'm glad that you are with us here, which is mostly of us, our geologists, exploration geologists, so they could, or we could learn from the expert about what the geometallurgy versus the metallurgical test, just like what you have described. Because sometimes we have some kind of mixed up between those two in regard to the stage, what is required at every stage. Thank you very much, Cristian.
Okay, Budi. Thank you for the question and for the clarification. And yeah, both metallurgy and geometallurgy are necessary, are complementary. They complement each other. Okay, maybe now we are in condition to understand or discuss in a better way this slide. Remember, we have this large sample in here for metallurgical purpose, this composite sample, 100 of kilograms, and we test different parameters, metallurgical parameters. Okay, we change the size, different conditions to look for the best combination of metallurgical parameters, and we freeze. Can you see? We freeze the geology. We freeze the geology. Here on geometallurgy, we freeze the metallurgy and change the geology. So for me, it's maybe rare, but this is my opinion. It's like the opposite, because we freeze the opposite. In one case, we freeze the process, the metallurgical parameter for geometallurgy, and for metallurgy, we freeze the geology and change the metallurgy.
One more question, if you don't mind.
Yep.
Is there any? Are there many offer printing systems in? Where are you from? Are you from Chile or from Peru?
From Chile. Yeah.
From Chile.
Yeah.
Okay. I used to live in Chile for about 4 years.
Yeah. Oh.
Okay, I was in Candelaria back then. Anyway.
Candelaria. Excellent.
Yeah. The question is, in Indonesia, there are so many, due to the geological setting, have lots of offer printing systems. So it is very challenging to actually identify the most representative samples for each stages or each system, because as you said, if it is not representing the ore or domain that we would like to get to understand the metallurgical behavior or respond, then that's going to be very misleading result, right? So what will be the best way to do that? Do we need to, like what we did usually, is do the geological domaining, meaning that if there are two or three offer printing systems, we will be collecting every single samples from every single system that not offer printing each other, and then we also collect one sample that's been considered as an offer printing for an offer printing zone for the ore body or something like that. Do you have any comments on that, Chris?
Yeah, I have 2 comments about it. The first comment is the following: there is not recite for a number of samples. This is the typical question as a consultant I receive. Someone asked me, like, okay, man, please tell me how many samples do we need? But it's not a simple question. And that's the reason why the international guidelines never indicate a number. If we check the GEORG, the NI 43101, the SK 1300, any international code, we will not find any number, any figure, like take 100 samples or whatever, okay? Because every reality is different. In that sense, when we have more complex deposit, unfortunately, we will need more density of metallurgical or geometallurgical sample, in this case, geometallurgical sample. So in some cases it's easier, we will need less samples. In other deposits, we will need more samples. Even if the variability in one deposit, if we have, for instance, you maybe Budi say something about this porphyry with this like lithocap, this high sulfidation on the top. Maybe the bottom part, the lower part, this porphyry style deposit requires less density of samples because the variability is lower. And probably the high sulfidation part will require more density of samples, since the high variability of this zone in terms of metallurgical behavior. The second thing I would like to say is more oriented probably to your question, is how can we define what we need to sample? What unit? How can we define the domains? The most common way to do that is, as you said, make a combination of all the main features of the deposit, such as lithology, mean zone, alteration. Sometimes this could give 100 domains based on the combination, yeah, of, I don't know, 5 lithologies, 6 alterations, and 4 mean zones. If we combine all of this, maybe we can reach almost 100 combinations. So we can sort these combinations based in, for instance, metal content. Metal content is better than tonnage, okay? In metal content, we sort this in metal content, and maybe we can reduce the list of 100 to maybe 30. And 30 of this 100 contains 80 or 90% of the metal. Yeah, because some of them are really marginal, really small in terms units or combination in terms of metal. This is one approach. It's very simple, but I would recommend that approach in this case, or in any case, for define the number, the distribution of samples, and what combination of domains to use for collecting samples. Okay?
Yes, excellent. That's exactly what we're facing and what we've been dealing with. And we actually came up with about tens of samples, but at the end it was finally decided to be reduced to 7 or 9 samples for 9 domains and 9 samples. So for sure, but yes, that's quite a challenge. Thank you, Chris. Oh, okay. Yeah, sorry. I have one more question, but maybe I will let somebody else to ask you a question first. Later on, if there is enough time, I'll ask more. Thank you.
Thank you, Budi.
Chris.
You're welcome. De nada. Someone else?
I think we've close to the end of our questions and answer session. So if Pak Budi still have one last question, maybe you can, Pak.
Okay, thank you. It's about the grade, Chris. We also consider grade as one of the parameters for our domain: high, low, and medium grade, or 2 or 3 separations for those. Is there any? I know it will be dependent on the ore characteristic or ore deposit characteristics, but is that quite common to have a domain based on distribution of the grade?
Yeah, that's a really good question. Yeah, it's very common, but in general, it's not the best approach to define units. It is better to take into account the geological domains, such as lithology, mineral zones, etc., than using these grade intervals. The best approach for the grades is, in my opinion, the next. When we take or make this the design of the geometallurgical campaign, we should let me think, maybe I have this. Okay, no, maybe it's going to be difficult to find, but the idea here is try to replicate the statistical distribution of the grade of the unit. If we have a unit, the unit A in zinc or gold, we have the distribution for that unit in terms of grade. So the idea is our samples, if the samples are 50 in that unit, these 50 samples more or less approximate to the distribution of the whole units. Okay, so we have a goal distribution in our unit. We need to replicate more or less the distribution in our samples. That's the idea. This is my suggestion. Instead, using intervals of grades or something like that.
Okay, thank you. Thank you very much.
You're welcome. De nada. You can find me in LinkedIn also, just in case. Okay.
Okay.
I will share with you the email. No problem at all.
Sure. Thank you so
Thank
much.
you. Thank you so much, everyone.
So summary, maybe as a geologist, we have a lot of information and technology that express the characteristic to give guidelines and warnings for the processing aspects. So this is a really an eye-opening session. Thank you so much. I will be giving the room to Reza.
Yeah, thank you, Nadira. And thank you, Christian, for a great presentation and the discussion. And we would like to thank you to all of the participants and the engagement to the discussion, and also for the STJ, Pak Fisco, and also Pak Farid for the insightful discussion.